Hi everyone, welcome again to our lockdown CPPC seminar. Today we have Laura Sberna from the Max Planck Institute of Gravitational Physics in Potsdam. So Laura did her master's at the La Sapienza University in Rome before going to the Perimeter Institute for a PhD. She's now a postdoc at this Albert Einstein Institute. And she's worked on various things from dark matter, particle physics, cosmology, as well as gravitational waves. And today she's going to tell us about gravitational waves. So thank you very much for being with us, and take it away.
Thank you, Kieran, and yeah, thanks for the invitation. As you said, in the past, my PhD started with work more in the cosmology, astroparticle direction, but in the past couple of years, I've worked mostly on gravitational wave problems. But since I know that the audience is probably more interested in cosmology and dark matter rather than astrophysics, I will try to make some connections with those topics. And this work is, the output of a couple collaborations, one with Tubiana and Miller, where Tubiana is currently a student in Paris and will join me in Potsdam as a postdoc soon. And the other collaboration is with a large number of LISA enthusiasts. I couldn't even write all their names, including Andrea, who's in the audience. So I'm going to talk about dirty gravitational waves, and I hope to explain what I mean by dirty in a moment. I'm going to first give you an overview of this topic, very broad, and then I'm going to talk about two specific examples or applications. So in this nice animation by Zoe Hare Doctor, you can see all the gravitational wave events that have been observed so far in the first, second, and the first part of the third observing run by LIGO-Virgo. So as you can see, by the size of the circles, so they represent different masses. So you can see that among the events detected so far, we have a nice variety of masses and combinations of masses. And these are black hole, as you might know, these are black hole binaries, a couple neutron star binaries, and now even a couple of black hole neutron star binaries. But I think this animation was made before, so they're not there yet. So they look like a nice variety, but really all these events that we've detected so far have something in common. And this is that we've been detecting them at relatively high gravitational wave frequency. And this means in turn that these binaries are very close to merger. So the two bodies are in a very tight orbit, and they eventually merge in the gravitational wave band where we can see them. And because the bodies are so close, the gravitational interaction between the two is really going to be the dominant driver of their dynamics and also the dominant imprint on the gravitational wave emission. And so these are well described by vacuum Einstein equations. But this will not always be the case, because in the future we will have detectors sensitive to lower gravitational wave frequencies. And as a general rule, this means that we will see objects on wider orbits. And if the objects are further away from each other, the gravitational interaction is not necessarily the dominant driver, and you can have non-vacuum effects becoming significant or even dominant over the dynamics. As I said, this is a general rule, but there are some exceptions, as we will see. More concretely, these events where non-vacuum effects will be important and which we collect under the umbrella term of dirty gravitational wave sources You can think of a couple concrete examples. One is the case of binaries where one of the two components is a star, so the matter is already present within the binary. So you can think of double white dwarfs, black holes, neutron star black holes, and so on. And the other example is the one in which the binary is made of two black holes, so there's no matter in the binary itself, but the binary is located in a matter-rich environment. You can think of, my favorite example is AGN binaries, so binaries in the dense accretion disk of an active galactic nucleus. And here I'm referring implicitly to binaries with similar masses that orbit inside the AGN. But another example is the one in which you have a single body that is spiraling into the supermassive black hole at the center of the AGN. And similarly, here you can have matter effects being important. But let me place these dirty gravitational wave sources in the frequency landscape of the future, present and future. So at low gravitational wave frequencies on the left, you can see detectors like the pulsar timing array and SKA. In the middle frequency, we have primarily LISA as scheduled to launch in 2034. And at higher gravitational wave frequencies, you can see again the ground-based detectors like LIGO and future detectors like the Einstein telescope. And together with their noise curves here, you have some of their potentially dirty gravitational wave sources. So on the lower hand, we have very massive binaries made of black holes at the center of galaxies. In the middle region, you have massive binaries that go from 10 to the 6 down to 50 solar masses for us. You have again the extreme mass ratio in spirals that I mentioned again, a smaller body orbiting a very massive black hole at the center. And then the galactic binaries, which are the star binaries that we mentioned in the previous slide. These are predominantly in our galaxies because their gravitational wave emission is not as intense, so we can't really see them at a cosmological scale. Well, all of these sources that I placed here, potentially more, this is not a complete list, can be affected by a number of environmental effects that go from accretion disk phenomena, where they are immersed in an accretion disk, or they're transferring mass between each other in the binary. You can also have third body effects where you have an external perturber. Of course, this is still within purely gravitational physics, but we still collect it under the dirty gravitational wave term. And at higher frequencies, this is a bit an outlier that is important at higher frequencies rather than lower. You have tidal effects between two stars or a black hole and a star. So now that we have an idea, a vague idea of what dirty gravitational sources are and how they're distributed in the gravitational wave frequency landscape, let me tell you how these dirty or matter effects are gonna impact the signal and therefore how we're gonna observe them. So primarily, we're gonna observe these effects as they directly affect the signal that we measure in our gravitational wave detectors. So imagine you have a chirping binary, which means that it's evolving significantly in frequency. Its frequency is growing over time. Then we can describe this binary, the gravitational wave strain in the frequency domain with an amplitude and a phase. And this phase, in vacuum general relativity, is predicted to have the following form in an expansion for small velocities compared to the speed of light. This is known as the post-Newtonian expansion. And here in this series, you can see that the terms have specific powers of the frequency to the 1/3 and multiples. And general relativity also predicts specific coefficients. So this is a standard vacuum binary. What happens if we have matter effects? Well, in general, these are going to introduce new powers of the frequency here, lower or higher. This is going to cause a dephasing when you compare a vacuum waveform and a non-vacuum waveform. This is what I'm doing in this plot. And of course, you can also have matter effects contributing to the same coefficients AN in some cases. I should mention that not all binaries are going to be chirping. Some binaries are going to have a very slow evolution in frequency. So we call them quasi-monochromatic, and we rather describe them in the time domain, where we expand in Taylor expansion the frequency with this f dot and f double dot. And these parameters can also be affected by matter effects in a similar way. And finally, while this was the direct impact of astrophysical phenomena on the gravitational wave signal, you can also have indirect effects that are not going to impact the single signal, or not in an obvious way, but are going to impact the population of binaries of a specific type. For example, the black hole binaries that we've already seen. But by this, I mean that, of course, these binary might not have any matter around them or in them, but they're still, the output of a long number of complex astrophysical processes. They can determine the distribution of their masses, their spins, their eccentricities, and so on. And so by studying their overall population, we can still learn about the astrophysical processes that came before. So now we have an idea of what sources we should have in mind and what's the effect of these dirty gravitational wave physics on these sources. The obvious question is, why should I care? Well, in the next few slides, I want to say that these matter effects can really be a blessing because of the number of different physics problems that we can tackle with them, from astrophysics to cosmology to dark matter, but they can also be a curse. But let's start with the positives. Well, the positive thing is the most obvious direct consequence is that we could gather a lot of astrophysical insights on how these binaries are formed, on accretion disk phenomena, where accretion is really a ubiquitous phenomenon in astrophysics that is, however, very hard to model in general because it involves a lot of complicated physics and a lot of different scales. In particular, we hope to learn, as you will see later in this talk, about active galactic nuclei. And of course, because we have gravitational waves, but also matter, we hope to have opportunities for multi-messenger astronomy. Well, the second positive with dirty gravitational waves is that we could do cosmology with them. So we could learn something about the evolution of the universe. I want to give you two quick examples. One refers again to the overall population of binaries. In general, from a gravitational wave, as you might know, we can only hope to learn the luminosity distance and the redshifted, so the observer frame masses. And therefore, we cannot disentangle the redshift information, and in general, you cannot make a standard candle directly from a pure gravitational wave observation. Well, when you have a population of sources, however, the population can introduce a mass scale because it might have features in it. So it can have a lower mass gap, or it can have an upper mass gap. And overall, by analyzing the full population, we can measure both these features in the population, but also infer the redshift information of the sources. This is what they did in this paper in 2020, I think. And as you can see, you know, they have some optimistic predictions for the measurement of the Hubble constant. You know, more recent papers say that this is not going to be obvious because populations can have complicated structures, they can have contributions from different channels and so on. But, you know, at least at an optimistic level, this seems promising. Another way in which we can do cosmology with dirty gravitational waves is by using the tidal interactions between two stars. This is because the way in which the tidal interaction affects the wave brings about a direct dependence on the redshift. At least if you use, you know, some interesting relations between tidal couplings at different orders. And then again, you can have some, you know, good constraints on the Hubble constant, at least in the future with, you know, future ground-based detectors like the Einstein telescope. Next, since I know that the audience is probably interested in dark matter searches, I wanted to mention that whenever I talk about in the rest of the talk an environmental effect, you can always imagine that the matter sourcing the effect is not ordinary matter, but it might be exotic or dark matter itself. So two examples of this are, well, dynamical friction from light scalar dark matter, or dynamical friction from particle dark matter. I don't know what the final word on this will be, whether, you know, these effects are really measurable in the future or not, but this is a still developing problem, as you can see from these two recent papers. Okay. So lastly, let me come to the negatives. Dirty gravitational waves can be a curse for, you know, gravitational physics people, because they can be confused with modifications of gravity. So the most interesting examples for us will be a time-varying gravitational constant, which predicts a modification of the waveform of this form with a frequency to the -13/3. And you can try to remember this number because it will appear later when we talk about, indeed, an accretion effect on the waveform. Well, of course, the hope is that these two hypotheses can be distinguished through electromagnetic observations, because we don't expect any specific electromagnetic signatures from theories beyond general relativity. And finally, I like to mention that these studies are bridging a bit, you know, more traditional astronomy or astrophysics and gravitational theory, and so you can always hope to, you know, uncover some new aspect by bridging two fields and doing interdisciplinary research. Okay, and to conclude this introduction, I want to mention that from now on, I'm going to focus on a specific gravitational wave frequency band and a specific detector, LISA. LISA is my personal favorite, and for dirty gravitational wave astronomy, it's particularly interested because it has, you know, a nice variety of sources that it will be able to see, most of them potentially affected by environmental effects. And the second reason why LISA is so interesting for our purposes is that some of the sources that we will see in LISA after a month, you know, a few days or years, they might migrate to the frequency band of you know, future ground-based detectors. This is known as multi-band gravitational wave observation, and it's particularly interesting for us because at different frequencies we're going to be sensitive to different effects, And by combining these two observations, we can get even tighter constraints on the low frequency phenomena. So if you don't have any questions, I'm going to move on to my first example. As I promised, I'm gonna give you a lot more details on two specific examples of dirty gravitational wave sources. The first one is going to be the one of black hole binaries of similar masses located in an AGN. And the two science goals that we're going to have in the back of our mind when studying these sources is first that we are interested in disentangling different interpretations for the formation of black hole binaries, the ones that we've already seen in LIGO and Virgo. The main formation scenarios that we will contrast here are the isolated evolution, where processes within the binary determine what the binary will look like at the end, and the AGN option, where accretion disk phenomena, or the overall distribution of sources around the AGN is going to be important in determining the population. And of course, if we can see directly the effect of the AGN on the single source, then we will be able to tell, yes, some sources are originated in AGNs. And the second science goal that we will have in mind is to study the AGN itself, and in particular the supermassive black hole at the center. Measuring the masses of these supermassive black holes can be sometimes challenging, and we hope to, with these observations, to give an independent probe of these black holes. And the third motivation for this project was a specific event seen last year by LIGO and Virgo. This was known as GW190521. You probably heard about it in the press and in talks. This was a very interesting event because the total mass was very high, above 100 solar masses. And at least in the vanilla interpretation of the data, one of the masses was, or both, were in the upper mass gap. So this was an event that was harder to explain with the isolated formation scenario. So this already hinted at a potential AGN origin of this binary. And then a potential electromagnetic counterpart was reported. This is not, airtight observation. It might not be related to the gravitational wave source, but nevertheless, this was an optical flare from an AGN, and so again, it kind of supports the idea that this binary might have originated there. So for us, we're not going to think of this binary in LIGO and Virgo. As I mentioned, we're going to imagine measuring, detecting binaries of this type, but in the future with LISA. And we're going to try to understand what we could learn from them. Well, the first thing you should know is that if a binary like this is located in an AGN, it's probably located in what is known as a migration trap. This is a location where the torques exerted by the gas disk balance each other. And so a lot of these binaries are going to accumulate in these specific locations that are relatively close to the supermassive black hole at the center. And so because we're very close to a black hole, another black hole, a third body, and because we're located in an AGN disk, so a dense environment, we can have both matter effects in these binaries and third body effects. So among matter effects, I'm gonna go through them more in a second, but you can imagine mass accretion onto the binary, dynamical friction, and natal kicks, and so on, that can increase the eccentricity. And among the third body effects, we can have Doppler modulation because of the orbit around the supermassive black hole, lensing, Shapiro effect, and so on. So let's start by the more matter effects, although I'm going to include also peculiar acceleration, and it will become clear in a moment why. So the first effect is mass accretion onto each of the binary components. So we have material coming into the black hole and changing its mass over time. So this phenomenon can be described, as I mentioned, in post-Newtonian theory, and we predict that the phase will have, this specific frequency dependence. This is that minus 13 thirds that I hope you remember from before, that can be confused with a time-varying gravitational constant. The second phenomenon on this slide is peculiar acceleration. This is related to the Doppler effect that I mentioned, but we're assuming for now that we're sufficiently far away from the supermassive black hole that we can approximate the acceleration as constant. And we're going to treat this effect here because, as you can see, again, we have a minus 13/3 frequency dependence, so it's natural to connect it to accretion. And finally, dynamical friction thankfully has a different frequency dependence, and so it can be disentangled from the other two, at least in principle. So what we found, we did a Fisher matrix analysis over actually the parameter space of GW190521, which we treat as our model binary, but of course we're not going to have exactly the same binary in LISA. So, and what we found is that, especially with a multi-band observation, we could measure, reasonable values of the parameters that appear in these three effects. The first is the density, 10 to the minus 10 grams per centimeter cube is a reasonable density for an AGN disk. And this F Eddington equal to 1 is related to accretion, and 1 corresponds to the limit, the Eddington limit for accretion. Although this limit is usually derived in with simplifying assumptions, and so we could actually have super Eddington accretion in principle. And the acceleration parameter epsilon is, associated with a distance from the supermassive black hole of about 1 parsec. I think I'm assuming that the supermassive black hole has a mass of around 10 to the 7, 10 to the 6 solar masses. This was, obtained with a Fisher matrix analysis, which is an approximate, estimate of the errors on these parameters, and treating the three effects as independent. But we also confirmed this result with a full Bayesian analysis using, I think, nested sampling for the sampling. Again, you can see the effect of multiband that tightens your posterior on your parameters. You can see that acceleration and accretion can be basically treated in the same way and cannot be disentangled unless, acceleration takes up a sign, because epsilon can be positive or negative, that is inconsistent with accretion, because F Eddington can only be positive. But what we also learned from this full Bayesian analysis is that the two phenomena can be disentangled, can be measured at the same time if they're present at the same time, which is very nice. So next, we're going to move on to the third body effects. First up, we have the Doppler effect. So this is, the simple non-relativistic effect of the motion around the supermassive black hole at the center at, at radius r and with orbital frequency capital omega. And this is very simple to introduce in our waveforms. We just shift the time by, this orbital time, well, the distance, the distance along the line of sight. Well, but although this is simple to treat in time domain, it's not as easy to incorporate in a frequency domain waveform. This is because, in vacuum, this is the dashed line in this plot, frequency over time is monotonic. And so we always have, a nice correspondence frequency to time, and we can use a stationary phase approximation when we Fourier transform the signal. But when the Doppler effect is present, we have, this wiggly line instead. So this relation is not monotonic anymore. It's not one-to-one, and we need to be careful when treating the signal in frequency domain. The next effect is strong gravitational lensing. Of course, this is going to be significant when the binary has the right inclination, compared to the line of sight with the supermassive black hole at the center, and when the binary is behind the supermassive black hole. When it's in front, we're only going to have, a related Shapiro time delay. And overall, the time delay for each of the two images that we can have in geometric optics is given by a geometric delay because these are longer paths to the detector, and the Shapiro time delay because of the value of the potential, the gravitational potential along the path. So this is one effect of lensing, and Shapiro, this time delay. But of course, compared to the Doppler modulation of the frequency time relation, this is a much smaller effect. You can see that I had, Doppler is in blue, Shapiro and lensing are in red, and I had to increase this by a factor of 1,000 to put it on the same scale. Although, of course, lensing depends on this inclination angle, but, an inclination angle of 0 is going to be very unlikely to be detectable. And just to clarify this plot, these shaded bands are regions where the binary is behind the supermassive black hole compared to us, and that's where the lensing effect is the strongest. But of course, lensing can also have an overall effect of magnifying the gravitational wave signal. For example, for the plus image, we can have, for the parameters we chose, about 10% magnification. And the two images can, have interference with each other, and they can create these beating patterns on top of the magnification. So overall, even though the Doppler effect is the dominant one, Shapiro and or gravitational lensing can also be useful to, introduce different dependence on the parameters and disentangle more information, even though their effect is much smaller. And this is what we did in this plot. We imagined we observed one of these binaries where Doppler and Shapiro are present. So we are at a more generic inclination where we don't have gravitational lensing, just to simplify things. And what we find is that we can measure the central black hole mass and the radius of this central orbit to a very good degree. As I mentioned, with Doppler, we couldn't have independently disentangled both the mass and the radius, and so it's useful to add this extra effect from Shapiro or lensing. And I think these are going to be competitive measurements of the black hole mass with other astrophysical techniques, and perhaps even improve on what these other techniques can do, because the most accurate of them often cannot go as far in redshift. Okay, so we hit the science goal of measuring the properties of the supermassive black hole at the center. Of course, real life is always more complicated, and when you have a third body, well, three-body interactions are super complicated, but in the approximation that we have an inner orbit and a third body, you can still have a lot of other effects coming your way. You can have, changes in the eccentricity, modulations of your, orbital inclination, of your spin in the binary. Well, in the case that we were studying, all of these phenomena were much suppressed compared to the dominant Doppler effect. So I'm writing this in terms of the orbital periods, for example. So these are much longer compared to the, well, to the Doppler, not the orbital period, the Doppler period in the waveform. But of course, if any of these other effects are going to be present in your waveform, they might also give you extra information. So for example, Yu and Chen argued that in the presence of one of these spin effects, you could also measure the spin of the supermassive black hole at the center, which is a very interesting information.
Talking about gravitational waves, a seminar.
I think you're not muted. Okay, so if you don't have any questions, I will move on to my second example. This is the case in which we have a dirty gravitational wave source, where now there's no matter around the binary, but there's matter inside the binary, because one of the two components is a star, it's a white dwarf. Well, we got interested in this type of sources because from the electromagnetic point of view, the observational evidence is somewhat limited. We don't have, a certified white dwarf black hole that we know of. We have some candidates in globular clusters like this X9. But in general, we don't know if the two bodies are really a white dwarf and a black hole. In particular, it could be a neutron star rather than a black hole. And of course, this is not the first time that a new class or, a class that was not observationally certified before is going to be, found by gravitational wave observations. Because in the past few days we've heard of these first two neutron star black holes. So these were also sources that were not known for sure to exist. The fact that the observational evidence is limited is because they're hard to characterize with certainty. But to be fair, they're also rarer compared to other binary combinations. So for example, compared to double white dwarfs, the expectation from population synthesis is, a few orders of magnitude below, although with large uncertainties, as you can see. But from a gravitational wave perspective, we can still hope to see some of these binaries because they will be brighter, because the black hole can bring more mass to the binary compared to a white dwarf. And therefore, even though the local rate might be low, we can enlarge our observational volume and hope to see them. So to give you a better idea of these binaries, you should imagine a white dwarf and a black hole that have come close together because of the emission of gravitational waves that has tightened their orbit. And at some point, they come so close to each other that the material on the surface of the white dwarf starts to spill into the region of influence of the black hole and form an accretion disk. So this is known as mass transfer in astrophysics. And to understand this, we can look at the balance of angular momentum losses and gains. So on the left, you have the total angular momentum in the binary, which is distributed between the orbit, the black hole, and the white dwarf. And of course, the black hole, for example, is gaining angular momentum from its accretion disk, from accreting material. And we're going to make the simplifying assumption that the white dwarf is cold and it's tidally locked, so always showing the same face to the black hole. And on the right-hand side, you have loss of angular momentum from the binary in the form of gravitational waves, as I mentioned, and also in the form of wind, because some of the material in this, chaotic mass transferring process can also be lost completely. Well, solving this equation together with a few other prescriptions, we can solve for the evolution of these binaries. So on the top panel, you can see the accretion rate onto the black hole, which mostly happens, in the initial phase and then settles into a quasi-equilibrium. The white dwarf, as a consequence, of course, is losing most of its mass at the beginning. But the interesting panels are these ones down here, at least for a gravitational wave observation perspective, because what you can see is that the frequency is decreasing over time. If you're not a gravitational wave person, this might be okay, it's decreasing. But usually the binaries that we see in LIGO and Virgo are chirping, so their frequency is increasing over time. And the reason why we have this different behavior here is that, the emission of gravitational waves is not the dominant driver in the dynamic. The dominant driver is the transfer of mass between these bodies, which is, redistributing angular momentum in the orbit and causing the frequency to decrease. And, from an orbital perspective, this means that the binary has come close and then it's going to move out again. Okay, so you can also understand that this quasi-equilibrium phenomenon here, because you're going to have, the radius of the white dwarf, its change is going to balance the change in this Roche-log radius, which is this region of influence here. But anyway, the best way to understand these binaries is not by studying the evolution of a single one, because we're actually going to see a large number of them, hopefully. So the best way to understand them is by looking at the evolutionary tracks of a lot of binaries, because in this way you can identify some common behavior. So in this case, for example, you can see that there's an interesting relation between the white dwarf mass and the frequency of the gravitational wave. So you can imagine that when we will measure, these signals, we will be able, from the simple measurement of F to infer the white dwarf mass. This was already known in the literature. What we added is this extra relation that now again involves the frequency of the gravitational wave, but also the frequency derivative and the black hole mass. And it's intuitive to see that with this extra relation, we can completely characterize the binary white dwarf and black hole alike. But of course, to be more precise, we confirmed this with a Mach-Lisa observation, where the binary is described in this quasi-monochromatic form because it's evolving very slowly. We were able to, measure F dot and F at these two, example frequencies. And from this, using the relations that I showed you before, we were able to infer all the properties of the binary. The white dwarf mass, the black hole mass, which we can tell, with confidence will be a black hole and not a white dwarf. And even the luminosity distance, which again, all of this information is might seem trivial from the point of view of higher frequency gravitational wave observation, but it's not trivial when the binary is evolving so slowly that its signal is so simple. You really need to understand, the phenomenon behind it, the complicated mass transferring phenomenon behind it, to be able to recover correctly all of these parameters. And this is just an example in which this was done for white dwarf binaries. And since they didn't have The second relation that I showed you earlier and that we found in our paper, they needed Gaia, so electromagnetic observation, to disentangle the three parameters. And they also found large measurement errors from this recovery process. So to conclude, I don't like to take too much time, but I just want to spend a couple of the last minutes to some project I have in mind for the future, and hopefully is more interesting to you as it is related to cosmology rather than astrophysics itself. So the idea is one that I mentioned earlier in the talk. If you remember, I said that from a single gravitational wave observation, we can recover the luminosity distance, but only, you know, the masses in the detector frame, so the redshifted masses. And so there's an implicit redshift information, but from a single observation, we can disentangle these two. Well, this is not the case when we have a matter effect. I mentioned before, tidal interactions can break this degeneracy. Well, also mass accretion can. This is because the effect in the waveform is proportional, depends not only on this redshifted mass, but also on the mass itself. So for example, if we knew the accretion rate, so this F-Eddington parameter, we could measure independently M, Mz, and the luminosity distance and disentangle the redshift. But of course, the accretion rate is not known a priori. You could imagine, observing this binary in the electromagnetic spectrum. But of course, if you already have an electromagnetic observation, you have the redshift, you don't need to do any of this. The idea instead is to use only gravitational wave observation of accreting binaries and use not a single observation, but again, a population study. In fact, you can imagine that the accretion rate will have, some distribution in your set of sources, and in particular, you can imagine that it will have, a sharp feature around the accretion limit that I told you about. In standard calculations, you cannot have F-Eddington above 1. So if this is the case and we study the population together with the cosmology, we can hope to measure the Hubble constant. Of course, this is still work in progress, so I don't know the answer, but we hope, to be able to place in the future competitive bounds on H0 using these dirty gravitational wave sources. To conclude, I think I will just leave the summary here, and I will be happy to take any questions if you have any. Thank you.
Great, thank you very much. That was a fascinating talk. Do we have any questions from the audience? Please just go ahead and ask. Didn't see anybody muting themselves. Maybe I'll start. So there was one thing. This may reveal my kind of ignorance about how LISA actually works, but you had this plot where you were showing the frequency as a function of time for, you had the Doppler effect, and then also this like Shapiro time delay where you're showing this sort of this sort of wiggles that it does. The thing that struck me was that the time scale. I mean, I guess this is just related to the binary itself, but the time scale was in years for this to be happening. And so is the idea that LISA would just be kind of continuously observing these over the timescales of years? Because I mean, the LIGO events, they sort of happen like that, right? Whereas, if we is LISA going to be sort of observing one of these at any one time, or will it be able to see like multiple of these happening at the same time? Because something taking years to happen seems like quite a different type of observation to LIGO, which is basically just waiting for these things to happen. So what is the general idea for how this works?
Yeah, and that's a very good question. Indeed, observations in LIGO, they're often, linked to kind of popcorn popping, because they just happen on very short time scales. And this is because we're seeing the binaries really at the end of their lifetime. We see them spiraling and then they merge. But in LISA, we're seeing them much earlier. They're still spiraling. And so they will continue to spiral for years, even hundreds of years, depending on when we observe them. And so this poses, a big analysis challenge, because you're going to have very long signals, so you need to be very precise in describing them, otherwise you're going to lose them. And also you're going to have so many signals at the same time, because if they're all long, they're all going to be present at the same time. And so actually this is still an open problem. We don't have a pipeline ready yet. A lot of people are still working on this.
Oh, that's interesting. Yeah, it's something that came into my mind just then, but yeah, I guess it does sound quite interesting. So also the other thing that I wanted to ask about was this: when you have this white dwarf black hole binary, and then you have this frequency dependence, which seems to be decreasing with time, and then so this time scale is in like 10 to the 7 years, and I guess we're observing it sort of, what does to us or to Lisa, would this basically just look like a sort of constant frequency signal? Like would you actually see this decrease?
Yeah, indeed. That's why I said that this will not be a chirping binary. We will treat it as quasi-monochromatic. Yeah, the frequency is almost constant, but actually, within certain values, we will be able to measure the first derivative.
Okay.
And that's the important information here, because if we only add the frequency, we wouldn't be able to, recover all the parameters.
Yeah.
So as you can see, if we go at lower frequencies, then f dot is even smaller, and therefore, this constraint is wider. And if we went to even lower frequencies, it would be hopeless.
And is it, for these gravitational wave experiments, I don't know about Lisa, but I mean, do LIGO or Lisa expect to have sort of backgrounds which are almost monochromatic?
Yeah, Lisa, indeed, most of these star binaries in our galaxy will form a background. I think if I go back a lot of slides, I can show you this here. Yeah, so these are all these galactic binaries, so many of them, and overall they form this background, down here. Because some of them will have, enough amplitude large enough for signal to noise ratio that we can separate them, but most of them will just make this background. Yeah.
What about like the non-gravitational wave backgrounds? I mean, just others. Are there any other sources of signal that Lisa would be subject to that might be monochromatic? I mean, like, I don't know, I guess you have like seismic noise and stuff like that for LIGO, but is there anything, what are the sort of non-gravitational wave backgrounds that Lisa would be subject to?
You mean these sources of noise? I think there's laser noise, and there's noise related to the motion of the aircraft, because this is in space. But of course, you're not going to have seismic noise, and that's why we're going to space for these lower frequencies.
Okay, that was what I was curious about. So do we have any final questions before we wrap up? Please go ahead. I might ask, just this isn't anything you mentioned, but I mean, some people are excited about gravitational waves in the dark matter community because there's a potential link to primordial black holes. I guess here we're kind of maybe we're less interested because the black holes that you're looking for are maybe more massive and are kind of ruled out. But are there any links that between you know, the stuff that you've been working on in primordial black holes that you know of?
So I guess the thing with primordial black holes is that there would be an independent formation channel, right, for the LIGO binaries. And in general, to understand these population formation channels, you want to have as much information as possible. So in LIGO, you get the spin and the masses. One thing that LISA can do is at lower frequencies, it can measure the eccentricity better. So if there's any link between, you know, the formation channel and the eccentricity, then maybe LISA will be able, you know, to help there. And then this is off the top of my head what I can think of, but yeah, maybe there's more.
Oh, cool. So if we have no more questions, I think I can